Yo, 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 what's up, everybody? Good morning, Harukanan. Good morning, Fabek. Am I feeling better? Yeah, better each day. Thank you for asking. Like, now it's the sickness is not as intense. It's just like low intensity, runny nose, annoying stuff, but good. Good morning, Tutu apps. So, as I said yesterday, we're done with the grass. I'm happy with how it looks for now. And today, we're gonna move on to pretty interesting stuff, I think. And I'm also a little bit scared. Ooh, let's see here. So it's probably going to be a lot of planning today and writing things down, seeing how to understand things, and less about implementing stuff. Because what we're going to do now, or the next chapter we're going to start, is water terraforming. So right now we can lower and heighten the ground, and we can add and remove grass. And now I want to be able to add and remove water, and we want this water to act in a pretty cool way. So let's see here. Just before the stream, I'm sorry about the slow start, by the way, but I created this new issue. And we're gonna pack a lot of things into this one. So this is purely water terraforming issue. I think I have some other water issues. Water interaction and water shaders. So this one is more visual, and this one is polish, I would say. This one, however, is actual gameplay, and it's going to be like the base of the system. Pardesi, what's up? Thank you for the follow, appreciate it. So let's do So, there exists two approaches to this one. I'm gonna write both down because I would define them as one that is easy and straightforward and one that is hard. The easy one is way less fun, but it will still do its job, while the hard implementation will be so much more fun to use when the player creates his or her garden. So like the main goal is to implement it the tough way, the more fun way, but it's also very nice to know that we can fall back to something simple if the hard part doesn't turn out. If it isn't doable, which I doubt, if it isn't doable for me, maybe a little bit higher chance, or if it's just not plain fun. If it's not fun, we can skip it and go to the more basic approach. And we're gonna call this first one basic. And it will pretty much, I wonder how I want to define these, pros and cons maybe. A basic water system which includes one big water plane set at a certain height. That's not how you spell certain. Certain height. if the player digs deep enough, the water plane will appear, basically. So if we just dig deep enough, we will have a water plane here. So it will basically look like this. What's up, Amiso TV? So this is one approach, and we'd probably like to skip the mesh collider on this one. Easy, boring. Incredibly easy. Let's see if we can add... Do I have some transparent object? Yeah, we're done with water. Let's move on to the next chapter. Let's see. Transparent prototype materials. Yeah, let's see if this one still works. Guess not. Or is it? It's game only. Do we have some distortion here as well? Yeah, we actually have distortion power and stuff like that. It doesn't really work as how it should. Well, we can go with this. Anyway. Yeah, so this would be the easy approach. Actually, we're gonna do... Yeah, so we'll get puddles at certain heights, like, so then you deform like this. It can lead to some okay mechanics, I suppose. It's water, at least. Okay. Do I want to define it as pros, cons? Yeah, it could be nice. Extremely easy to implement. Performant, definitely. only allows for water at certain heights. Does not allow for rivers, which is actually a half lie. It does allow for rivers. We can do some basic river physics here, but it's not rivers going up or down. So it does not allow for proper rivers. An advanced? A advanced? I don't know. An advanced? Should be an here. Yeah, only allows for water at certain heights. Only allows for water, or does not allow at certain heights, at specific heights. Does not allow for yeah, different water levels, or like only allows for water at pre-specified heights. Honestly, this one is the one that weighs the heaviest against this one. And honestly, this might be a little bit too strong of a wording. Because I remember Viva Pinata does this system, and like, it was still semi-fun, but it could be way better. What's up, Dark Summon? Long time no see. Yeah, overall I'm good. I've been fighting this low intensity cold for a while, but other than that, nothing to complain about. How about you? Fabic, well, you could have some defined water area height that should work. Yeah, so the idea here is we pretty much define during compile time, like water will be at level X, and then you can dig down to X and you can dig more down. So this system allows for water of varying depth, but the water level will always be at a certain height. Nice. Keep up the good fight. I try. And good to hear. What's up, Namida? An advanced water system relying on some type of... What was the correct word for it, Fabic? Water... step fill algorithm. Flood fill. Thank you. Some type of flood fill algorithm to dynamically calculate water levels at different areas or at different positions, basically. which would allow for let's see, we want to do what a mistake. Which would allow for, we're actually gonna add a plane as well. This would basically allow for we could create a water hole here, but let's make it like this maybe, and then we could go and do not the prettiest, but we could do it like this. Jesus, that's rough. Okay, this was a little bit harder than I anticipated. I need to work on this marker a bit, but it would allow for something like this. That's rough. I want to change the height of the terrain. Yeah, or check the normal values to determine the water flow. Yes. So we're probably gonna pack a gradient, some form of gradient texture into one of the channels, so we always know which direction, like, so we can go, if we have 1 pixel, we can quickly figure out which direction is down. Main question, is the player be able to create water, or it will be determined by surface level? If we go with a entirely dynamic system, the player will be able to place water basically. That's how it's going to be. So we could allow for, let's see. Jesus. Something like so we can have this mountain area here. It's a little bit too steep for my liking. And then we need to figure out amount as well. We could have a little bit of a pool like this, and then we do a fuck, there's a lot of things that need to be thought about here. Which will lead to water running down here, like oop. Or you can place a water source that dynamically create the water flow. Exactly, like before we deep dive into the actual implementation of it, we need to define a set of rules, like how exactly will it work? What's up, Arnav? I think and good morning, PG King. I'm thinking about the system that okay, so an advanced water system would probably rely on some sort of, at the base it would be some form of voxel system. So we have terrain data is actually just like a texture with a low resolution texture where each pixel defines the state of the terrain at a world position. And when it comes to water, I'm probably, like, when we develop this system, we're probably gonna have one whole texture that is for water only. It will give us more data to work with, because I don't know how much data we need, but for instance, something data I would want to hold at least is how much water is at a certain how much water does a certain pixel contain, and that is going to be defined by the terrain height is the bottom right, and then the amount of water defined by the player, and then using that data we will fill neighboring pixel based on that one. So for instance, let's say that we have a hole that is 2 times 2 pixels, so 4 pixels. The player clicks one of those pixels, or at one point in the world, and then we add 0.4 amount of water for that pixel. Our flood fill algorithm will fill the neighboring pixels, so it will flow. It can only flow in 3 directions, so it will divide the amount we have into those directions, and we will end up with 4 pixels with 0.1 water value. Something like that. That's just a first. Yeah. And yeah, the texture will hold data and not color. Yeah, we're gonna do this as well. To do. Define different approaches. Define for water, I would recommend checking all 8 neighbors of a pixel. Yeah, that's probably what we're gonna do. So it's gonna be a lot of interactions and a lot of iterations. Like, I don't care that much about real-time dynamicality. Is that a word? Like, I'm entirely okay with a water system that has different stages. So we have the water system is in a stable state, and then the player adds more water sometimes, and then it enters a recalculation stage, which is offloaded to some other process, and then we can let that calculate in the background while we just animate the player adding water. And then when that pre-calculation stage is done, then we know how the end result will look for the water, and then we can just do some nice animation from current state to end state. So like, a fully dynamic system would pretty much be as long as the player is adding or removing water, we recalculate the water dynamics at all times. But I would be okay with the opposite, where we have different, like the first one I explained, if it makes any sense. What's up, Cypher? Yeah, that's the one I'm okay with avoiding. So 100% written from scratch fluid sim. I did write a 2D fluid sim years ago, or I did, like, I think it was like heavily based. I wrote my version of Joe Stamp's fluid simulation in 2D, and it was advanced. Do I want to split it up? Basic, advanced, hyper advanced. Let's do basic, medium. I still want this one here, advanced. A water system, oops, to calculate water levels. State-based water system. An advanced water system relying on some type of flood fill algorithm to dynamically in real time calculates water levels at different positions. This one is probably what we're gonna lean against. Definitely way less math for 2D. That third dimension really fucks stuff up sometimes. Most of the time, honestly. So this one is heavy focus on state-based. So player goes to a point, adds or removes water. We do a lot of calculations behind the scene while we obscure them in nice fancy animations. The calculations returns with a finished result of what the water state will be, and then we take the current state of the water and that new state of the water and animate between those two. That's pretty much the medium approach. In fact, like, best case scenario, this, but like depending on how this one goes and depending on like my understanding of the whole thing, we might give it a try. But yeah, that damn third dimension, indeed. And then we haven't even started talking about the fourth dimension. There's a very cool YouTube channel where someone is making a 4D game. I don't remember what it's called. But yeah, that damn third dimension. So flow or scenario. The player selects a point where water will be added or removed. The point and amount is passed to a secondary thread calculating the new state of the water in the garden. Some transition in some way. Yeah, this is going to be one hell of a task. Have you thought about using particles for simulating water and generating mesh from the particle bounds? Like, when it all comes down to it, that is basically what we're gonna do. So like, each index in the terrain data texture will be sort of a particle, but it will be a big particle. Yeah, when it all comes down to it, it's basically going to be a voxel water system a little bit more complex than the Minecraft one. I hope that's the goal. What it all comes down to is we add X amount of water at a certain position, and then it's up for the algorithm to calculate how to spread that amount of water out in an area. And Fabic, you just made this Friday way better. Thank you so much for the donation. I appreciate it. Thank you so much. Said it before and will say it again, well deserved. I appreciate it, Yeah, I'm gonna do my best and we'll see. Hopefully you will think that way after you have seen the final water system as well. I want to add description. Yeah, we want to write this down in a nice step-by-step way as well, but I just want to try to explain it real quick. What it all comes down to is the underlying data structure is basically a type of voxel object or type of voxel matrix. Let's see, 3D matrix. But the X and Y dimension let's see here. But where only the X and Y value defines position, while the Z value defines water amount slash height. Just that you know, I'm going to find every edge case you missed. I welcome it. I want to get those. I want to know about those edge cases, you know. So let's see here. Does this make any sense? The underlying data structure is basically a type of voxel 3D matrix, right? Usually you have I don't know, maybe not the correct terms, but X and Y defines position. So we basically have our two-dimensional terrain data. X and Y indices are position, and the value we have in those pixels, so Z, defines the water amount, and then it's up to our algorithm to spread that value amongst neighboring pixels. And if this is everything we have, then we can just pack this into the blue channel of the terrain data. I actually like that. So right now we have height in red, grass, which is green in the green channel, and water, which is blue in the blue channel. But might not be enough. And then we could pack, if that would be enough, then we could pack the gradient into the alpha channel, which will affect water flow, possibly affect the grass as well. We'll see. But yeah, we're gonna take a look at this, definitely. And if I remember correctly, so I did implement a basic fluid simulation way back when, and they always talk about different states of it. So you have a stable state of your fluid simulation, basically. So if you affect the if you add more X to the simulation, then it is in an unstable state, and it will always, if implemented correctly, it will always converge towards the stable state. And this solution, so the medium approach, it's basically that we never show the unstable or unstable state to the user. We have a fluid simulation in a stable state. We add more water, it becomes unstable. We calculate the new unstable state, and then we show the new stable state to the player. While this one would show each iteration of the fluid simulation stable or unstable. Arnav, what is name of character in game? So it's the goal is that the player will decide the name, him or herself. But the current, and also alter the appearance a tiny bit, but the current character we play around with right now is actually named Bob. What's up, Ferda? God morgon. Be water, my friend. Yeah, I try, but it's hard. So yeah, that's pretty much the difference between this one and this one. Like, do I want to have appendix terms? I need to do some googling here, but right now we're gonna define our own terms. Hey, it's my document. And we're gonna do stable state, unstable state, stable simulation state, unstable simulation state. Yo, what's up, Derek? Hope you're having a wonderful Friday so far. What we're doing today, we are starting with the water terraforming. First of all, it's going to be a lot of planning today, essentially. It's pretty much going to be all planning. Because we need to define the system before we start implementing it. And right now we have three different approaches to this problem. The basic one is the most boring one. That's just plane-based water. So water at certain heights. You have to dig deep enough to make water appear. Then we have the two more advanced, and they include fluid simulation, but extremely basic fluid simulation. Think Minecraft. The simulation, the simulation is in a stable state and does not change. The simulation is in an unstable state and changes each iteration. Yeah, let's just have them there. So this approach, the fluid is in a stable state, the player adds water, the fluid becomes and turns into an unstable state. We hide the unstable state for the player and just calculates the new state. When we have the new state, we transition from the old state to the new state in some way. While this one doesn't hide the unstable state, we just show it for every iteration. We have some yeah, okay, so this one is 2D, I guess. Let's see. Beautiful. Let's do appendix terms. Yeah, like honestly, what it all comes down to is this. This is basically what we want to do. But we also want to reduce the amount we fill with. So if the bucket fills all neighboring connected pixels with the same value, we also want to reduce the value as we iterate through the algorithm. But we also want to do it based on terrain height, right? I want to draw some scenarios soon, I think. But it's hard to draw them in 3D. But just to visualize like my thinking process right now, let's do this. Oops. 2, 5. That's a pretty good grid. Can we do snap to grid? So if we have a two-dimensional system like this, and the player adds and let's say that the player adds water of an amount of 2 to this position, then we want to fill this one up and we want to fill this one up, but then that's all we have basically. So moving in the up and down direction will be free for the water, like that's our amount. Moving in the X and Z direction will cost. In this example we only have the X direction and then we have the value dimension. But if the player fills this position with a value of 3, then we basically want it to fill, it's going to fill this one up to a cost of 1, this one with a cost of 1, and then it's going to fill this one as well with a cost of 1. So now we have filled it with a value of 3, but the iteration of the fluid simulation will look at its neighbors and check, oh, we have this one and this one free. So we want to take the value we have here, or we want to fill these based on this value. So now we have 3 voxels we want to fill, but we only have a water value of 1, so we will pretty much fill these, all of these 3 with 1/3 each. So if the player add water with a value of 3 at this point, this is the end result we will get. And yeah, if we think about the problem in just 2 dimensions, and then we can complicate it by adding the other dimension, it becomes way easier. So right now we only have one position one position dimension and one value dimension. But then again, we can take the scenario if we have something like way harder. Maybe not way harder. If we would just define it by the properties we defined here, it won't be that much harder to do it here. We will probably end up with some water here and something like this. But that is also a pretty boring end result. So all we have done now is we have complicated the problem, and the end result, like the only thing that differs between this solution and the basic one, this one, is that we allow for water puddles at different heights. An end result I would like to see here would be, should I maybe switch the color for water as well? An end result I would like to see with this example would probably be something like this probably. So now we have some water here, we have some water here, and we have a constant flow of water. So yeah. So it basically comes down to this water fluid simulation. We want it to we broaden the definition of stable states to include stable states that appear to be unstable. Like a fluid simulation here would just take amount of water from here, put it here, and then we're done. So yeah, a stable system would lead to something like this. But I want to I want to let the player be able to create rivers. But rivers imply unstable. So yeah. So it would pretty much be something like this. When we do the iterations here, let's say that we fill here with a value of 5. We get up to here, it costs us 2. It costs us 2. And then we try to fill this one, check the neighbor, so on, so on. So maybe we can fill down to here, and it costs us 5. So let's say that we only get to about here with the water. So all of this is what we spend. That means that the stable state is actually, we have a river here that dries out. But let's say, for instance, that we fill this one with 8, a value of 8. That means that when we get to this point, we still have 3, a value of 3 left. So then we fill up to here maybe, and that's all the values spent. And that's our stable state. So basically, compared to this one, what we do here is here we spend values, and spent values are spent and unchanged, while here we spend values, but a value of 1 that is spent here will actually in the next iteration move either here or here. So we want to rely on a system that, like, if my rambling doesn't make any sense, it's probably because it doesn't make any sense. So yeah, feel free to interrupt or whatever. If we want to get to a result like this, a spent value is spent and unchanged, while if we have a fully dynamic system, a spent value is initially spent and then changed, moved around. And when I talk about values, it's water amount. And then if we get a stable state like this, we can do some pretty things. So we check the water value here, and we see that it's in a decline. So we use a river water shader for this part, and we use a lake water shader for this part. The state is stable, but in a realistic fluid simulation, this state would have been seen as unstable, because you would have more of this water would eventually end up down here. Yeah. How would this work in practice? It relies on yeah, it pretty much relies on oops. If we put 5 into this voxel, this one gets filled up with a value of 1. That's the maximum amount of water a voxel can hold. So we have 4 points to still spend, so it checks its neighbors, first in the x direction. So we fill this one up as well. Now we have 3 points left to spend, but we don't have any more neighbors in the x direction in this case. So then we need to spend it upwards. up. This one is full, this one is full. Yeah, we need to average it out in some way. What's up, Little Miss Murder? I saw an interesting YouTube video on Numberphile about the volume of cones. Feel free to link it. I feel a little bit weird saying it, but that sounds interesting. Now, basically what we're gonna have to do when we get to this point is we check this one, and before we set this one's value, so we add a value of 5 to this one. Before we do anything, we check its neighbors in the x direction. Okay, we only have one neighbor that is empty, so that means that we have 1, 1 here. And then we have 3 points left. We try to add it upwards. I wonder if we want to do it by the source. So then this one, we check neighbors. Oh, we have one more neighbor, we have one neighbor. We have one neighbor, one more 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 neighbor. So then we have a value of 3, which we want to split between 1, 2, 3, 4, 5, 6, 7, 8, 9 pixels. 3 divided by 9, is that 1/3? Yeah. So then we just fill these with 1/3. That's a very easy approach. But best case scenario, a more unstable state that we want to define as stable would include this one and this one and this one having a little bit more of the total value. So if this approach leads to all of these pixels having 1/3 of a water value, I think a better case would be this one, and this one having 2/3 each, and these having 1/6. So when we get a neighbor to the right, we split the value evenly. But if we move down as well, we want to increase the amount this one gets. But that would screw it up. That would mean that we get this value here, then this one becomes higher. This one has the same, higher, and then we get to this one, higher. So something like this. We split the remaining points between these pixels again. Only these 3 has the most water amount, these 2 have a little bit less amount, and these have even less. Something like that. But it will screw up rivers a bit, I think. So we're gonna have to do something like, if we check the neighbors and we go down, we just want to make the amount higher when we reach a new low. Thank you for the link, by the way, Little Miss Murder. It kind of approps to what you're doing. Ooh. Yeah, I haven't even started talking about terrain that looks like this. yet. Yeah, we're gonna have to implement this algorithm in a few different ways. So this one is the most easy. State. Then it's just about yeah, it's all about moving in the direction of the fluid value, so y. Then we have to take, so lower voxels located further down based on the height map will have to take precedence. So if we start filling up here, we check first in this direction. Yeah, this is going to be one hell of an adventure. Let's see if we get some more ideas. I would love to be able to rely on, let's see, two-dimensional water fluid simulation. Yeah, that's Joe's dam, I think. SPH, stay. Okay. Yeah, I don't think we want to go this deep, honestly. Oh, I remember this. This one would, like, if we successfully implement it, it would lead to results like this. Ours is a little special case. Like, I want a fluid simulation that goes against real world physics, basically, because we want to allow for downward flowing rivers that defies physics. Like, you could do a hack. You could implement GeoStam fluid simulation, and then you could add a constant influx of water here and a constant outflux of water here, which would mean that the water level here will rise and rise and rise until we get to here, and it will fall down here. The water level here will rise and rise and rise, but thanks to this it will stay the same. And this will receive, or that will end up with this state, but it will be an unstable state that just keeps on giving. So if we would implement the GeoStam's solution and we do influx outflux and then we just iterate it every frame, we would get the result we want, but at the cost of performance. Extreme cost of performance, mind you. Like this, I implemented this one, I think I even have it on my GitHub, and it's costly to run, it is. I'm just gonna save this link, by the way. It's, even though that's not the solution we might go with, it's extremely we have cmu.edu. Little Miss Murder, what neighborhood model are you going to use for leak testing? Yeah, that's a good question. Like, the best way to think about it is, or I think, so we basically have a grid. Let me just paint this very nice grid here. So we have a texture that tells us how much water is in each pixel. So we could probably have... So we have this texture, X and Y here says the X and Z position in world space, and each value in each pixel is supposed to be the amount of water in a value between 0 and 1. 0 and 1 will be remapped later on to height, min, and height max of the terrain. So if we go 0.2, so this would pretty much correspond to watch from the other dimension or other angle, corresponds to something like this. More for X, Y, and von Neumann for Z. Yeah, let's just say this. I have a lot of reading to do this weekend. Are there any free plugins that already do this for you? There might possibly be, but not with my data, I think. Implementing a data transformation might be easier than doing everything from scratch. Might be. A worst case scenario, we spend a couple of weeks on a third-party plugin for water simulation, and it turns out that it's neither working in our use case or the performance is insufficient. Yeah, we're gonna do some research this weekend, definitely. Like, once again, we don't want this to work like real world physics. Why not both exactly, Fabic? Like, we haven't really defined all constraints we want on our water system just yet, so starting to go shopping for third-party solutions is a little bit preemptive right now. Like, once again, we don't want real-world water physics. We want this scenario to be possible. Like in a real world, without a constant in-stream and a constant out-stream, this would never be possible. But we want it to be possible. We want to be able to build water objects at different heights with interconnected rivers in a stable fluid state. It's an extremely weird constraint, but a fun one, I think. And that, like, this makes me think that just a very, very simple cost-based fill algorithm will do the job. Like, we add some cost to going to in these directions, we add some cost going in this direction. Yeah. Animated plane. Yeah, that's what we had. That's our most basic one. And I think we're pretty much done with that one. So that's the solution we're gonna rely on, worst case scenario. Done. Not so... not very fun. But yeah. Could one do something like... So we have a value of 5 from the start, we add it here. So then we just check just in this dimension pretty much. Okay, we have 2 pixels, so each of them get this divided by how many they are. So 2.5, 2.5. That is too much for each of these. 1 is max, so that means that the water must go up. So we go up here, up here. You calculate all of these. Here we have a total of 1.5 extra for each of these, so that's 3. 1, 2, 3, 4, 5, 6, 7, 8, 9. So 1/3 for all of these. But then we check, oh, this one we have more below here, so we move it down. We have more below, so we move it down. So we get 1/3, 1/3, 1/3. Then we want to set 1/3 here as well, but we can't, so we move down to here. 1/3. We want to set it here, but we can't, so we move down here. We want to set it here, but we can't, so we move it down to here. 1/3. We want to set it here, can't, 1/3. Same here, 1/3. Kind of a good result, but then we get to this one and this one. So we set 1/3 here and 1/3 here, and that's wrong. So that would mean that we get water like this. But then, so for each of these new ones we check. Yeah, this is after the first iteration of our algorithm. Then we take this value and we check neighbor. This one already has a water value, we don't care. This one does not. So we try to add this one to this one. Or actually we take this one. This would be a never-ending algorithm, but it would give us a good result, I think, because yeah, then we check. Something like this. Just project it down for all of these. Which means that we get 1/3, 1/3. One-third. One-third, yeah, we'll have 1/3 here. So the problem we have now is we have this value which shouldn't be here, we have this value that shouldn't be there. All other values are fine. So then I guess we want to go here. In some way we want to reduce these down to 0 and make these be more. That's all we want. Oh, by the way, got some news. Baby arrived last night. Damn. Some news. That's great news. Congratulations, Cypher. Congratulations. What is a toke, by the way? Gonna go for a toke. Yeah, congratulations, man. A smoke, I presume. Yeah, that's probably correct. Enjoy it. Enjoy the talk. One activity I always look back on fondly with my newborn was just laying in the sofa with him on my chest watching TV. Like that is probably like one of the best things I know. Congratulations. Now, back to this extremely boring thing in comparison. The fluid sim. Favik is having a smoke with him. That is one thing I did my best to avoid, right? Okay, so this one, like a type of falling down algorithm, we just need to be able to solve this issue. Because if we take a look here, 1/3, 1/3, 1/3, down to here is okay. We just need to figure out how to take care of this value. How to spread that one out. And like if we could let this one iterate through eternity, we're gonna converge towards 0 for this solution. Because okay, let's say we have this state. We have a third here neighboring to an empty. So then we go in this direction, so then we check all of these. So we actually have a value of 1 in total. So we split up 1 between all of these, and do we have 6? Yeah, we do. So we end up with something like 1/6, 1/6, 1/6. And then we try the falling down again. So this one is already entirely fall down. This one falls down, this one falls down, this one falls down. So then we get through 1/2, 1/2, 1/2. So now we're basically at a state where we have Now we're basically in a state where we have 1, 1, 1/3, 1/3, 1/3, 1/6, a half, a half, a half, 1/6, 1/6. Okay, so yeah. Okay, so if we just continue this one, congratulations, we have a realistic water simulation in 2D space, basically. This one is going to continue to go down together with this one and this one. They are going to converge to 0, 0, 0, 0, 0. and these ones are going to converge to something. Doodle, I assuming you want varying water heights instead of one single water volume across the entire terrain. Yes, exactly. So this water implementation we have going right now, this is what we want to avoid. Like, we don't want our water to work like this. But also we want to allow for one body of water here and one body of water here and a constant stream of water down there. We want an algorithm that converges to a stable state which includes unstable properties. And that's one of the constraints that fucks us up the most, I think. Okay, so just going with the falling down algorithm leaves us with a result that is semi-real world like. So we need another way to solve this problem. Right now we're only playing around with x, z position and water amount, or height. So we're just playing around with x, y, z. If we have gradients, if we introduce gradients as well, so slopes and stuff like that, could we use it? Could one think about a solution? I guess one could think, but could a solution? Ooh. Could a solution where one calculate curves work? It's all how one handles this. Oh, that's a good point. You need to decide whether your water depth will increase or not if you terraform the valley to be deeper. Yeah, I think I'm visualizing a system where like I think I'm visualizing a system where the amount of water will never change unless you add... Ah, fuck, that's true. The amount of water will never change unless you add water or add dirt. Oh, that's a good point. Yeah, like at the beginning of today's stream, I might have mentioned this is going to be one hell of an adventure. Slowly and surely we're going to converge toward how we want our water to work. It's not set in stone just yet. So with that said, I think I only want to change the amount of water in the garden if water is added or dirt is added. And by that I mean, if we terraform here, for instance, let's say we just add ground here, then this amount of water will be removed from the scene, and we're gonna have to recalculate the water, so it would be something like this. So that's one scenario where the water level will change. The other water scenario would be adding more water here, which will make this one higher and this one higher, maybe even this. Adding water or adding dirt. So that means that if we, for instance, get to this point and we dig deeper, then we're gonna have to adjust the water, and in this case it would be adjusted down to here. The river will be removed, but this one will remain, basically. Does it make any sense? Perhaps the water depth can be a function of the number of influxes. So, yeah. Like, best case scenario, I think I would like to avoid influx points and outflux points or whatever. But it would be acceptable to include them. What you're drawing is not true. If the water is still there, will be no river. The water will fill the hole and the right container will be full. What's up, Shohan, by the way? Yeah, that's true. That is what we had a drawing visualizing previously. So that's something we have defined already. We don't want our water to work as it would in real life. We want to be able to support a stable state of an unstable fluid simulation. We want to have, yeah, like, so what you're saying is entirely true. You are exactly correct. So if we would go and paint this once again, if we add water here and we add it to an amount of this, we will get a river down here, and eventually we will get something like this, right? This would be the realistic end result. This would be the realistic stable state of the fluid simulation. We don't want this. We want to be able to have a stable state that is... Actually, I want to have this the correct stable state still here. So we're gonna draw this and we're gonna draw this. we want to be able to have a stable state that's like this. So when we step through our fill algorithm, we want it to be able to end in a state like this. I got the reason you're doing it like this, it's better for game water simulation. Yeah, like the end result is the player will be able to terraform his or her garden a lot, and I want to allow for the player to be able to create rivers. And unless you have a never-ending influx and a never-ending outflux, you won't be able to support rivers. But I want to be able to support it even though those things are not true. Yeah. So yeah, it's a little bit of a special case scenario we're working with, but hopefully I think we can come up with a nice solution. I think. So, let's see. Think about what happens if you have multiple influxes. You need to choose a neighborhood. There's more. I need to look into what were the two algorithms you were mentioning earlier, Moore and von Neumann. We're gonna go ahead and do Moore, von Neumann. I don't know them from the top of my head. But yeah, so like it's basically just hit testing for neighbors. So like when we talk about neighbors in our system, a voxel is always going to have 8 neighbors. Always. And those neighbors holds position in X and Z and height value. Like we want this water system to work with our terrain data we have set up. Terrain data, 2-dimensional textures, red channel height, G channel we can just skip, that's just grass related, B channel water amount. So this is a problem of let's see, we can define the problem like this. We want to do water simulation. We want to do water simulation on a height map where the only influx or outflux of water is player driven at a point. So we will never have more influx of water than 1. And we want to fill this grid based on a height map. That's basically what we have. But with a big constraint that we want to be able to support non-realistic stable states. It's one hell of a problem. Like, let's do this. New, let's go with 32 times 32. And is this actually the one we want? Looks a little bit weird. Is it based on... Yeah, let's do... Yeah. Let's work with this one. It still looks very weird to me, but whatever. Let's, for instance, let's make it a little bit easier. Let's go with white, and then we do... Maybe this will make the problem a little bit easier. Or add some light on the problem, rather. Udoramo, thank you so much for the follow, by the way. Appreciate it, appreciate it. So let's say we have this height map. White is max height, black is minimum height of our terrain. So this is basically what we have. This is the data. Each pixel, can we get a... Can we show the grid as well? Configure grid, what do we have? Did I selected a bad value? Let's go back here, scale image 32, 64, 128, 256. And then we do configure grid. Is it, did I 4 times? No, 8 times. There we go, beautiful. This is our height map. 1 maximum height, 0 minimum height. Each pixel is 1 voxel, we can call them. We get X and Z position in world from pixel index. We get height from the red channel. Basically what we want to do is we want to make a fill algorithm that based on an influx fills based on height. So easiest Does this even make more sense? So with an influx here, we want the water to disperse here. Some of it will come down here, and here we have a local minima, and we will get a little bit of a puddle here. We won't get any puddles up here or whatever, so our stable state is here. This is still like, however I think about this problem, since we want to support stable rivers like this, some sort of algorithm like this should be what we can rely on, right? Evgeny, what's up, by the way? Is it reasonable to separate the logic for lakes and rivers? Rivers can just be considered as a connectors for lakes. Definitely. Like in some way, we're going to do some sort of separation, possibly. But the question is, when in the process do we want to do the separation between lakes and rivers? So like yeah, like this is the hardest part. We want a fluid simulation that can converge towards a stable state, which, even though we don't have any influx of water, results in a river. And like that goes against real life rules, right? Rivers implies taking water from one position to another position. Like that's not stable at all, but we want to support it. And what will happen if you connect river to lake? Basically, like a river in this game will always be from one lake to another lake. We won't support rivers just ending. So a river, by our definition, a river must always go from one lake to another lake. Shoham, maybe the approach should be similar to Minecraft/City Skyline solutions. I don't know about City Skylines, but Minecraft definitely. They mark water in some places as a water source, and then from there water will flow until a limit. I like the sound of that. Although I must say I have managed to break the water in Minecraft. The water in Minecraft is lacking in some cases. That's what is it called? The new engine. Okay, so that is another case, Fabic. That's true. If we have one lake, we have a river from that lake to the other. Fuck, I need to write down all of these scenarios. Definitely. Let's see. But Shoham, thank you for the recommendation of City Skylines. Definitely gonna check out City Skylines, how they solve it. But actually, Now I'm starting to lean against the solution. Like just implementing real-time fluid dynamics, Joe Stamm's solution. This one I know works very good. And then we add some rules to it. Like if it's stable enough, we freeze it and create our own meshes representing the water. So if we solely rely on Joe's stamps, implement Joe's stamps solution. We have an influx. We have an influx here. So if we continue this influx, we will eventually get forever. We will eventually get water like this. But if we go down, down, and down, and we find a new low, then we can introduce an outflux. And then we let the simulation run with this outflux and this influx until it's semi-stable, and then we freeze it. And we have our final result. Right, so it's just we do a real life water fluid simulation, but we add additional rules to it to be able to freeze it at certain points. If two lakes have a connection, then you can divide the volume of water between them according to some logic. Yes. Yeah, like doing the Joe Stamm solution with custom-made constraints can eventually lead to a stable state including rivers, but that would be the least performant solution. If we have two lakes and have a connection, we divide the volume. So we could do, we add an influx of water here. Depending on the influx, we calculate the minimum points, so points like this. So we calculate this minimum point, we calculate this minimum point. So then we have two minimum points that are connected, and then we connect them with a river based on some logic, right? So we have an influx of X, we have a depth here of H. This one is closer to the influx, so we have some influx variable. We have this one, this has a depth of H2. It's further away from the influx, but based on the influx value, this one will still get water. So if we do the algorithm, we focus on just calculating minimum points, and then when we have found those and the appropriate water levels to those, that's when we connect them with a river that obeys physics. Yeah. Are you now drawing constant water flow from the heightened part? Yeah, like our end result, we want our end result to be this, as if we always add water here and always drain water here. But we want the end result to be this without adding and removing. And Shoham, they have water surrounding the map and rivers that are already in the map, and you can dig rivers from those water sources. Okay, so the surrounding water always they work as the water source, and when you dig your own rivers, you basically define new drainages from a never-ending water source. What will happen when you drop some water in the higher hole? It will fill it and the rest will go down the slope. Yeah, so let's say that we have this state. The player adds some water to no water. We get to this state and the player stops adding water. Then the player gets here and starts adding water again. It won't be any different. Like, then we will do this, our solution, but we already have some water values here. So I think it would be similar to the initial state, only that the player has a higher influx of water. So one could say that we have an empty case here. The player adds influx of water, we get to this state. Then the player comes back here and add more water, which gives us a state like this. There's really no difference between these two scenarios than if the player would just get to here and add more water the first time. So yeah, he will add some amount to the ground. I'm trying to avoid talking in influx points that always exist, because I want to avoid that. Like, the only time we get an influx point is when the player decides to add water. That's the only time this is relevant. And this is more a definition of add X amount of water at, or add W amount of water at point X, Y, Z. Or actually, in our case, a X age Z. So think about it like this. In a very crude, unpolished scenario, the player just goes to a point, clicks that point, and instantly water will appear. But behind the scenes, the player click is like the start point of our fluid simulation that calculates the new state of the water in the garden. And when that's done calculating, we just show that state to the player. Like, if this game would support a continuous water simulation for a garden this big, we would be running at, I don't know, sub 1 FPS. We just want to use, we want to go from state to state. But yeah, I think focusing on the minimas, defining minimas in some way, and then recreating the rivers after that. But it will be improved in game 0.2 indeed. I think what makes this problem interesting, like what makes this problem not about reinventing the wheel, is this fact. But I'm pretty certain like someone has already done this somewhere. But like, this is the fact that takes us apart from a pure fluid simulation, a correct fluid simulation. Yeah. Reinventing the oval. Yep. Reinventing the star-shaped wheel, pretty much. Or dare I say it, we're moving so far away from how water works in the real world that it's pretty much reinventing the square wheel. That's it. Yeah, it's gonna be a lot of planning it and thinking eventually, but look at this. Let's try this. It feels like I'm always going back to the let's see here. What did we have? We had, oops, I want these to be thicker. Oops. Could one do a solution where we add, like each square here, I just need to redefine it, each square can only hold at maximum 1 water. So the water value per square is between 0 and 1, right? Could we say that we're gonna do an easy, let's say that we want to add just in this example, let's say that we want to add a value of 3 to this point in the world. So then we take this point in the world and we go downwards if we can, but we can't. So we stay here. And then we go up 3 steps. So we add a value of 3. So 1, 2, 3. We end up here. From this point, this is so damn similar to what I've been reiterating so many times. But so now we have a value of 3 here. Then we check this dimension here. So we get this full line. And then we just copy that value. So each of these has 3. So then we go downwards from that. Or actually, if we do, okay, so we add 3 here. So 0, 1, 2. And then we add 2 to all of these. So all of these has a value of 2. Right? And then for each of those we start going downwards. So 0, 0, 2, 1, 0, 0, 0, 1, 1. Yo, what's up, Devs Bias? Hope you had a wonderful stream, and thank you so much for the raid, as always. And you too, you too. And welcome to all the new viewers. We're currently exploring the world of water. Can it hold less than 1, or is it binary? That's a good question. So a voxel can hold a float value between 0 and 1. The maximum is 1. So what can we actually do with this one right here? What does this tell us? Here we have found the minimus. Here we have found the minimus. The minimum points. So what do we have now? We have so we know that these are our water minimas. We have our source here, so these two are way closer to the source. And then we have these 3 points that are further away from the source. They are on the same plane, so we want the same value for all of these. So we take the average position, so this one, and then we take the average position of this one, and then we compare distance to source. So that gives us, I love just winging algorithms like this. So then we know that the closer to the source we are, the more water it should be, but it's also based on the full size here. So this is, yeah, so based on some variables we multiplied this one and we multiplied this one, so we might get something like this. So then we know our actual minimus, but yeah, maybe something. Robin, check out Octree. Yeah, we're definitely gonna do that. Good morning, Desai. Good morning. I love the current approach for making the rivers. You mean the lack of rivers? Asmith, hey man, just wanted to pop in and say thanks for sharing your thoughts on mechanic versus art development as an indie dev. I just finished my first satisfying shader after days of torment. Congratulations. Been there, been there. It's a powerful feeling, isn't it? Yeah, so now, like, with this approach, we can probably calculate the lakes in certain areas, but that's not enough. And this is just for this specific case. Let's see. Octree. Do we want to be more specific? Okay, so octree is just a binary tree, but with more children. 8 in this case. And then we have quad trees with 4 children. I see. Ooh. So I love that this is the default shape we use now for testing, for thinking about this. So if we add water here, we add water of a value of 3, we get to here, or we add a value of 3, so we get here, and then we take all of these neighbors in this dimension, and then for each of these we calculate lower valued children basically. So this one has 1, 2, and this one has 1, 1, 2. So this one has 4 children. This one has, in fact, do we want to go to the left and right as well? I don't know. This one also has 4. This one has 0. Now we want to go in this direction as well. So this one actually has 1, 2, 3, 4. 1, 2. So 4, 4. What do we have? 4, 2, 6. 0, 1. 4. Then could we use this information to our advantage? Like if we, for each point, we calculate how many voxels do they have beneath them, neighboring voxels. I want to complete this, see what kind of result we get. 4. If we just go to 6. 4. 1, 1, 2, 3. Yeah, the question is if we want to spread it out eventually. Yeah. So 3, and then 3, 2, 5, 3, 8. 1, 2, 3. Yeah, what disturbs me here though is that this one has a lower value than this one. But yeah. Decide what are we trying to solve. By the way, we're just in the beginning of implementing water terraforming in our garden, and this is going to be one hell of a problem, a fun one. Pretty much we want to end with unrealistic water simulations like this, or like this. Yeah, we want to be able to add water to our garden, and the water should behave in such a way that we can make lakes and rivers. Yeah. But I like this. I like the start of this. So if we add water here, we just go straight up, or the highest point here based on the influx of water, create a line, and then we go downwards calculating number of neighbors in some way. Felion PL, but water moving would be just graphical effects. In reality, it would be calculated once to establish its position and then just rendered over and over. Exactly. So we're in the state where we just try to arrive at the data point. Oops. Like, where we just try to arrive at this state, and then we will, when we have this state, we will generate a mesh based on the state, and then we will add shaders to it. So this will actually just be a plain like mesh, but the shaders will make it look like it's flowing. So that is definitely true, but we're still in the state where we try to arrive at a good water state. The player will be able to add and remove water, so every time that happens we need to recalculate this state and regenerate the mesh, and then we're at a stable state again. Could we have amount of moves available representing how much water we have, and just a star path find every pixel of water from the source? Yes. Like, that's actually a very good. So I've thought about if we could use a path find algorithm for this one. Oops. And then our cost would be it's all about also easiest case. So we start adding water here, we add 5. So we have a value of 5 here, and then we walk using a path find, we walk from this one, and we lose values every time we move out. 4.5, 4.5, 4, 3.5. Yeah, so maybe the values might not be correct, but something like this, and then we do 2, 1, 1, or 0.5, 0.5, But a path find, we're eventually gonna end up with, like, if we use it just how it is, we're gonna end up with some path. And if we have this path, let's say yeah, the hard part, so a star path, sorry about this, it's always finding the best way from one point to another point, right? Based on some values you define. What we want to do is, we could actually, if we go with 5, or if we use this as a start position, we just want to, how far away from this point can we, what is the furthest away we can travel from this point? In this two-dimensional example, we would add a very hefty sum to go up, and it will be cheaper to go in this dimension, right? So then we might get something like this. Then we can't get any further. And then we can just I don't know. Flood fill is pretty much going to do that, I guess. Yeah, definitely. So a flood fill. Like a lot of these algorithms, it's been a while. So they just don't come to me. Yeah, flood fill is probably the best one yet. Maybe I'm not in context. What's up, by the way? But if you drop 5 points of liquid, then it must be 5 points of liquid in some, but in different cells. Yes. With the exception that we want to support but yeah, that's true. So if we drop 5 points of liquid, we want the sum of the result to be 5 points divided by the number of cells we affect. And it's always going to be cheaper to go in this direction. It's going to be free to go in this direction. Or something like that. Me too, Fabic. Sometimes it leads to weird scenarios where you plan and you try and eventually you just arrive at some algorithm that someone else has already done, like flood fill. But yeah, flood fill is 100% going to be what we go with, I think. No, not 100%, I don't want to be... But we're gonna do flood fill, which is similar to a path, right? I'm only on my 9th interaction of my terrain system, I know the struggle. Yeah, but it's a fun struggle. Yeah, we want to do some flood fill algorithm where we flood this one outwards, and it's always cheaper to go in this direction, more costly to go in this direction. So we always want to flood downwards. So like if we get to this point or this point and we have the possibility to flood here, 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 and here, and here, and here, we always want to choose the cheapest one. Or like, then it's more towards a star path. Depending on how we define the costs, we'll probably get something like unitoid. Should we consider pressure? No. So that is also something I've been meaning to do. Oops, sorry about that. For a while now. We're gonna set in stone the different things we care about and the different things we have to work with. And I think I can pretty confidently say that we work in a voxel space, and we care about the amount of water in a voxel. We want to take gravity into account in some way. So like, you shouldn't be able to have one voxel with water above one that doesn't have water. Dasai, thank you for the link. I will check it out after the stream. I appreciate it. We'll just copy and save it. Thank you for the timestamp as well. If you have a pixel of water, you move it bottom always. If impossible, you move it sideways. Otherwise, you move it top. Yes, that's the rules that we want to have. You mark spot as occupied and spawn another pixel of water. Yes, so that's a binary system. Our voxels will always be able to be filled with water of a value between 0 and 1, so a floating point value between 0 and 1. But it's actually not a bad idea to simplify the problem initially. This was a loud song, one sec. So if we simplify the problem to be a binary problem, first and foremost. In this case, what I'm a little bit afraid of in this case is, so let's say that we just use one. So we have a 5 value here. We try to go downwards, we can't. We try to go here, we can't. We try to go here, we can't. Okay, so we can't move downwards. Can we move to the side? Not here, but we can do it here. So then we move here, which leaves us with 4 here, or 1 here and 4 here. We do the same here. This one is already marked. We can't move downwards. We have to move up. This one is cheaper than this one. So we move up here. We leave 1 here and we have 3. We do the same calculations. Can't move down. We need to move here. So we leave 1 here, we have 2 here. And on it goes. We leave 1 here and we get to 1 here. So we get water shaped like this. I wanna... five. So we have one, 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 and now the struggle begins. So right now we have a voxel here that has an empty space close to it. So then we go then we need to go from this one. I wonder if we can do... We track its path to its next stop. And then when we have this stop, we know how many voxels we have. So 1, 2, 3, 4, 5, 6, 7, 8, 9. So 1/9, 1/9, 1/9, 1/9, 1/9, 1/9, 1/9, 1/9, 1/9. And I guess this is an okay result. Yeah, the top layer will always be the one between 0 and 1. That is correct. Yeah. Fabric, what will happen if you will have one voxel that can go down in 2, 3, or 4 direction? Will it split or select the one while the lowest normal? Yeah. So we can look at that as well. You could think... No, actually, if we do this and we add a cost, so we have 1 here and we start Can we hack this? So as long as we have above 1 in value, we always want to leave 1 and go onwards. I don't know. In this situation, we could assume there is no square 2-2 hole. We just have 1 pixel water to move to local minimum. Yeah. Oh, fuck. Honestly, this has been... Even though I haven't written 1 line of code today, I think we're like... Slowly but surely, the end result is getting clearer and clearer. And we're gonna do this. So, unfortunately, I have to run now. But I will continue this one on Monday, and hopefully with a little bit more knowledge in place. Yeah, I still think we made some nice progress today. And I'm gonna do my best to research it more this weekend. because now I have to run. But thank you everybody for watching. Thank you for all the input. I appreciate it. And thank you once again for the donation, Fabic. And yeah, have a great weekend, everybody. And hopefully I will see you on Monday. Peace.